Bifurcations. So, talking about bifurcations, I'll briefly recap what we've been talking about so that we can continue from where we left off. Talking about bifurcations in 1D ODEs, and we discussed two of them. So, we had this general system dy by dt equals f of y. We had a standard procedure. We said find the fixed points, then use the fixed points to linearize the equation. So, fixed points we denoted y star, linearize the equation about y equals y star. That was something we did, and then based on this the stability was given by this linearized equation, and this k depended on dou f or df by dy at y star, right. We did the Taylor series expansion, and then that was the first term, and we kept it in order to determine the stability of the system, and then this gave us some information about whether a fixed point was stable or whether it was unstable, and how fixed points attracted trajectories, stable fixed points attracted trajectories, unstable fixed points repelled trajectories, and so on. So, we discussed all of that, and then we went on to the next question, where we asked how do fixed points change their stability. So, for that we discussed this saddle node bifurcation, and here you had two fixed points, and then they came together and then they annihilated each other. The standard prototypical example, was given by this, and we said lambda minus by square, or even b equals 1, does not matter, you can rescale. I am just going to write it as lambda minus y square. A and b can be picked. A is lambda, of course, that is the parameter, and we said as lambda was changed, and when lambda came to 0, that we call critical lambda, there was a change, qualitative change in the behavior of the solution. That is really what we mean when we say a bifurcation. Two solutions, which is one stable, one unstable, now suddenly both are missing after the bifurcation point. So, there is a qualitative change in the nature of the solution, and so this happened. We drew a bifurcation diagram as well. So, we plotted y star as a function of lambda, and then we got something like this, or the opposite depending on the sign. So, whatever one of them, and that is what a saddle node was. And then we said that any ODE that showed a saddle node bifurcation could be brought into this form by some suitable change of variables. Okay, we call that the normal form, and then we moved on to a second type of bifurcation, which was a transcritical, which looked something like this, lambda y minus y square. Here we had two branches, again these also had two branches, again y star as a function of lambda. Now, again the two fixed points came and came towards each other, they met each other, but then now they exchanged their stabilities after they meet. Okay, so, that is what happens here. It is different from the first case. And then we also said that just using a geometric picture of a line representing the phase space, phase line, and two billiard balls representing, or two cricket balls, whatever, representing the two fixed points moving as you change the parameter. These are the only two possibilities that can happen physically in this case. Okay, so, that was the situation. Now, what we will do today is we will talk about the third possibility, which is when you have three fixed points, which is called the pitchfork bifurcation. And we will see that there are two different variants of the pitchfork bifurcation. This is somewhat subtle, but they are very important variants. and we will discuss the normal forms. We'll analyze them just like we did over here. It's fairly straightforward. The procedure is the same, and I'll talk a little bit about where these bifurcations come up, and then we'll start working out some examples. Okay, so that's the plan for today. We'll look at two nonlinear ODE examples, and then we'll see how to analyze them using the new information, the qualitative schemes that we've developed now. Okay, so that's our plan. Good. Now, in order to be able to do this, let me first write down the normal form for a pitchfork bifurcation. Just like this, these two are normal forms for these two bifurcations. Turns out the pitchfork has two variants. The first one has an equation like this. Okay, notice we had two fixed points for the saddle node, we had two fixed points for the transcritical. So, both the right hand side f of y had two y star solutions. So, it was a quadratic equation. In one case it was lambda minus a square, in another case it was lambda y minus y square. So, there were quadratic equations. Quadratic equations, when you put f of y equals 0, give you two solutions. So, two fixed points. Now, and we realize that there is nothing else that can really happen with two fixed points. Now, we are going into three fixed points. So, we need a cubic equation at least. Okay, we can have a higher order, but cubic is the least we need, and so I have this y cube term. I have not included a y square term for good reason. You can, it turns out, and we'll maybe explore this a little bit in the assignment. It turns out that you can reduce something that has a cubic term to something that has a quadratic term to a form analogous to this with a few changes. The nature of the bifurcation will change. They become what are called imperfect bifurcations, and they are not as clean as this case, but okay, we'll stick with this case for now. Okay, good. So, for this case again we do the same procedure. We find the fixed points, fairly straightforward. This is one fixed point, obviously is y star equals 0, that is a trivial solution, and you have two more, which is y star equals plus or minus square root of lambda. Okay. So, now you have 3, 1, 2, 3, 3 fixed points. So, the first step is fairly trivial. The second step is to find the linearized version. So, linearize about y star. Now, the complication that we have now is we have to linearize about 3 fixed points. We have 3 of them, we have to do that separately. So, let us linearize about y star equals 0, the first fixed point. So, this is df by dy at y star equals 0, and then this is eta. So, df, this is f of y, remember that is f of y. So, df by dy is just lambda minus 3y square, and when you evaluate this at y equals 0, this gives you just lambda. Okay, so, df by dy is lambda. Okay. What about the other two fixed points? For y star equals plus or minus square root of lambda, we have df by dy is again lambda minus 3y square, and that is lambda minus 3 times y square. Remember, y is plus or minus square root of lambda. So, y square really does not matter whether you are using plus or minus, it will just give you a lambda, it will be minus 2 lambda. So, both of these fixed points have the same value for df by dy. Okay. So, that is good. So, that tells us now that the stability is as follows. The y star equals 0 has df by dy equals lambda, y star equals plus or minus square root lambda, both have df by dy is equal to minus 2 lambda. So when lambda is positive, then that means y star equals 0, this one is positive, so it's unstable. Okay. When lambda is greater than 0, then the other two, which basically have the same stability now because there is no sign change, these 2 points are both stable. Okay, because both have minus 2 lambda, lambda is positive, minus 2 lambda is negative, so it's okay. So again, remember what we said, the function when you have 3 of them taken pairwise, they have to be positive, stable, unstable, stable, unstable, and so on. They can all be stable or all be unstable because the function cannot just do this well. So you see that is the case here. Okay, so the origin fellow, which is presumably in the middle, plus or minus square root lambda on either side. If you draw the phase space, this is y, this is the origin, plus or minus square root lambda on either side. Origin is unstable, so it's an open circle, and these are stable. Okay, both are stable. Good. That is for lambda is greater than 0, of course. What happens when lambda is less than 0? What happens when lambda equal to 0? So when lambda equal to 0, this becomes lambda, this is 0, this is 0. The position of the fixed points, all 3 of them merge. Y star equals 0 is the same, it's unchanged. These 2 are coming closer and closer to the origin, they merge with the origin. Okay, so fixed points merge. But if you continue lambda further, make it lambda less than 0, then the merging of the fixed points has an interesting consequence. Firstly, y star equals 0 because its df by dy is plus lambda. When lambda is negative, y star equals 0 becomes stable for negative lambda. So before it was unstable, now it's stable. And what happens to y star equals plus or minus square root lambda? When lambda is negative, you have only one real solution to this equation, the fixed points. These two don't exist because lambda cannot be negative for these two to exist, right? So the 2 other fixed points now disappear, only the origin is left. So again, there is a qualitative change in the nature of the solutions. You had 3 fixed points, now you have only 1, and the stability is also changed. So it's a bifurcation point. Lambda equals 0 is a bifurcation point. Okay, just like before, same idea. So let's draw this bifurcation diagram now and see what it looks like. Oh, incidentally, this pitchfork is called a supercritical pitchfork. Okay, so let's draw a figure, a bifurcation diagram for this case. Remember what that was? You take y star on the vertical axis, you take lambda on the horizontal axis, and when lambda is positive, we had all 3 were allowed. You had 3 fixed points. These 2 were stable, so square root lambda, it goes like this, parabola, and they're solid lines because they're stable. And y star equals 0 was unstable. Okay, and at lambda equals 0, that's where the solutions come and merge and so on, and then lambda less than 0, you only had 1. So this is what the bifurcation diagram looks like. Okay, and you can look at this, and this is presumably why it's called a pitchfork, because it looks like a pitchfork. Yeah, so this thing is a pitchfork. You can, like, this is a tool. Yeah, I don't know if people have seen a pitchfork before, but yeah, that's a pitchfork. Okay, so you have 3 fixed points, 2 of them disappear, and the third one changes stability at the bifurcation point. Okay, so it's a bifurcation in that sense because the qualitative nature of the solutions has changed. Okay. Good. So now we'll just for the sake of finishing up the algebra, we'll just do the other pitchfork and then we'll come back and analyze and sit and think deeply about what we have said so far. Okay. So far I've just been, going off on this random trajectory of drawing phase space trajectories and finding fixed points, stability and so on. These are fairly algebraic things. It's, physical interpretation of this is not quite perhaps clear to some of you, but we'll come back to that once the algebra is complete. Okay, so that we can grapple with the physical consequences at once. Okay, so this is for supercritical. Supercritical pitchfork, and again any system that shows a supercritical pitchfork bifurcation can be reduced to this normal form, so to speak. Okay, just like we had for saddle node and transcritical. Please bear with me. I'll just do a little bit more fairly standard algebra, and then we'll come back to the physical consequences. Like I said, let's take another one. Now, if I change just this sign, I make this plus. Okay, this is the next example. Supercritical had a minus. Now I'm going to make a plus there. That is called the subcritical pitchfork. I've just changed one sign, lambda y plus y cube instead of lambda y minus y cube. Again, this is a third order equation, so it should have 3 solutions. So you expect 3 fixed points. Let's go ahead and do our usual algorithmic scheme. First, you find the fixed points. This is lambda y star plus y star cube equals 0. So you get y star equals 0 is another fixed point again. The other two are plus or minus square root of minus lambda. Okay, so you have minus lambda now, and this is what you get. Now it seems like, okay, we just made one sign change. Maybe whatever happened in the supercritical case for positive lambda will now happen for negative lambda and vice versa. Maybe that's something you can a priori think of. But the situation is a little bit subtle and needs a little bit more investigation. If you do the linearization again, presumably about y star equals 0, doesn't matter. You only need df by dy. df by dy from here is lambda plus 3y square. The value for y star equals 0 is just lambda. For y star equals plus or minus square root minus lambda, the value is lambda plus 3 lambda square, and lambda square is minus lambda. Y square is minus lambda. So that will be lambda plus 3 into minus lambda. This is minus 2 lambda. Okay, so we've got stuff that looks similar to what we had before. Only there are some subtle sign changes that have crept through. Okay, and that's what will make all the difference. So again, we plow on ahead. We see what we can do. So for stability, step 3. For lambda positive, let's do lambda negative now. Okay, let's start from lambda negative. So when lambda is negative, you have 3 fixed points because minus lambda square root will give you 2 values here, 1 value here. So all 3 fixed points exist, but, and remember that was the opposite. For lambda positive, you had 3 fixed points in the supercritical case. Now for lambda negative, you have 3 fixed points defined, but there's a small change. The change is here. So when lambda is negative, y star equals 0, whose df by dy is just lambda, becomes stable. It's a little bit different from here, right? Because here when the 3 solutions existed, the y star equals 0 was unstable. Now when you have 3 solutions existing, this is for lambda less than 0, the y star equals 0 is stable. Okay, and naturally, just because this has the opposite side, the other 2 fellows become unstable. Okay, so the thing is flipped. Not only is it flipped with respect to this, but the stability is also flipped. Okay. Again, lambda equals 0, same thing happens. as before, the fixed points come and merge together, and for lambda greater than 0 you have only one fixed point, only y star equals 0, the other two don't exist, and the y star equals 0 when lambda is greater than 0, the df by dy is just lambda, so this is unstable. Okay, so you have the mirror image of this. If I drew a bifurcation diagram here for this case, I have y star, I have lambda. Now for lambda less than 0 you have 3 branches, these two are unstable, so it's going to look like this. This guy is stable, so it comes here, and then this guy becomes unstable. Okay, so the two outer ones are unstable, the inner one is stable, exact opposite of this. So two outer ones are stable, inner one is unstable. They approach each other, and then they finally come and meet at the origin, and then when they meet the origin, the stability of the origin changes from stable to unstable here, from unstable to stable here. Okay. This distinction is very important because this is what makes all the difference in a practical setting. This is called the subcritical pitchfork, and you get it from the supercritical just by making this change. Okay. Now, subcritical pitchfork comes up in several situations. But before we get there, we have to understand the physical consequence of these bifurcations. So far, we've only been talking about, like I said, y star, lambda, and so on, and purely in algebraic terms. So we've been able to take some simple derivatives and say a few things on linearization. But what does all this stuff mean? Okay, so let's put this together. So what does all this mean? Okay, the first step is, remember, we go back all the way to the start. We have a ODE, autonomous ODE. Let's take an autonomous ODE for this case, and we have an initial condition. We have a domain 0 to, let's say, T1. That's our domain of interest. So this is a system. We've specified it completely. It's non-linear. So okay, some function f. We don't know what it is. Let's say this is my phase space. This is the origin. So I start at y naught somewhere here, and then I look at what happens to the trajectory. Okay. This is, if you solve the equation, you get y as a function of t. And let's put a parameter in here. Let's put it explicitly. So you have lambda. Lambda is a parameter in the problem. It could be some coefficient, it could be some physical parameter, whatever. And so the final solution depends on lambda. It also depends on, let's say, y naught. Okay, that's the initial condition, whatever. Okay. So that's the full solution we have got. So in the ideal case, again going back to that hierarchy that I keep barking about, in the ideal case, the closed form solution is known. So you know y is a function of t in this form, and of lambda in this form, of y naught in this form, and so on. But it's here. So all the stuff is encoded here. So I start at y naught. That's here, and then I see how the trajectory traverses. Does it go this way? Does it go inward? You know, was it going this way? Whatever, right? Depending on where I start. So it's either going to do this or it's going to do this. It can't do both. Okay, so one of the two. So if I start at y equals y naught, is the trajectory going to go towards the positive infinity direction? Okay. Now, all the stuff we've done so far, if we know what f fixed points are there and the stability, if we know the position of the fixed points and the stability, then we can ask the question, if I start, if we, okay, I said we, okay, if we start at y naught t equals t naught, then what happens as t goes to, okay, I've said t1, maybe I'll just make it infinity, it doesn't matter, t goes to t1 or t goes to infinity, whatever. That's the question we can ask. Okay? And not just that, we can also ask a deeper question, and how does this answer change if we change lambda? Okay, so what happens if t goes to infinity is the first question. Second question is, I have a parameter that is there, and how does the changing of that parameter, how does that affect the answer to this question? So this is like a sort of steady state solution to the ODE, and you want to know what happens. Now remember, right now we don't have this. We don't have this expression. This is okay. It's good if you have this expression and everything is moot. You just go and use this expression and say whatever you want. But we don't have this expression. We only have this. Okay, you only have this. Somebody has given you a differential equation, and then they say I'm starting at y naught, and you want to know what happens as t goes to infinity. Where does the solution go? Okay, maybe you're interested in the steady state solution of this problem, and so you want to know what happens for very large t. Okay, and you can answer that question. So for example, if you find, what do you do to answer that question? Well, you go back step 1, 2, 3 just as we did before. So you go step 1, find the fixed point, step 2, find the stability, step 2 linearize, step 3 find the stability, right? So step 1 gives me, let's say, 2 fixed points. I'm just using an example, you could have 3, 4, whatever. Step 2 I linearize and I get something, and step 3 I get that this is stable, this is unstable, let's say, okay. And for some particular value of lambda, this is what the situation is. Okay. Now depending on where I start, depending on where exactly y naught is on this line, the answer to this question will change. Why is that? Well, if y naught is here, let's say my origin is somewhere here, this is the origin, let's say this is y naught. If y naught is here, then as t goes to infinity, since this is a stable fixed point, it's going to attract all trajectories towards itself. So as t goes to infinity, if you start over here, you're always going to reach the fixed point eventually. Okay, that's how you use this information. Again, you haven't solved anything in the ODE, you only found this 3-step process and you've done all this sort of algebra, simple enough algebra, but it already gives you some information. Okay. What happens if y naught was not here, but it was here? What if this was y naught? Same thing. This attracts all trajectories from this side, all trajectories from this side. So if y naught was here, then if I started here, this trajectory is eventually going to go and reach this. So as t goes to infinity, I will go and reach this fixed point. So y will be this as y goes towards this fixed point. Let me call this y star 1 and y star 2. If y naught was here, this is what will happen. Okay. Similarly, what happens if y naught were not here or there, but it was actually here or on the left of the origin? Okay. What happens in that case? Well, in that case, the trajectory has no way to get to the stable fixed point because there is an unstable fixed point in the way. So the unstable fixed point tends to throw out these trajectories, it tends to repel them. So whatever starts here will start going out towards minus infinity. Okay. So in this case, t goes to infinity, y goes to minus infinity, unless there is another fixed point somewhere else. If there is another fixed point, if you extend this phase space all the way and then you find there's another fixed point here, this is possible, of course, because pairwise they are opposite, stable, unstable, stable, and so on. If there's another fixed point here, then this trajectory will leave and come over here. So again, then your solution to this or answer to this question will be this. This fixed point is where it will go as t goes to infinity. Okay, so just by finding out the fixed points, solving an algebraic equation without doing any calculus, remember that's all we have done for y, f of y equals 0. You only solved an algebraic equation. Just by solving an algebraic equation, you can now say everything about the long term behavior of the solution for any arbitrary f, any arbitrary nonlinear f. Okay, it can be the most horrific looking nonlinear expression. You don't have to solve it in closed form, you probably can't, but you can do this stuff. Now, for the first order system, this entire procedure seems a little bit of an overkill, because remember what I said when you had a first order system, going back to that original hierarchy, we said closed form solution, quadrature slash series, qualitative, which is what we are doing, then numerics, right? That is the hierarchy. If you just have an autonomous first order system like this, you can just presumably just do 1 by f of y equals dt and integrate both sides, right? In principle, you can do that. F of y could be a horrible thing, but then you get this t plus c, you have some horrible looking thing on the left hand side. You have to integrate it and then you have to invert it. Okay, so if you had a complicated function here, you could have the integral of that function end up being something like sine of y plus y cube equals t. Now you have to write y as a function of t, so you have to invert it, which is non-trivial. So you have two non-trivial steps, and it's a little bit painful to do. But in principle, this still can be done. So for a first order system, doing this and doing this probably is equivalent, because there you have to solve an algebraic equation, here you have to do an integral. Depends on which one you are more comfortable with. You can do one or the other and get the same information out. Okay. The problem is when you go to second order systems, and again we are doing this with a view of illustrating how these things work for second order systems. That is our main goal. If you go to second order systems, then things become a little bit more cumbersome. This procedure will no longer work, because you can't just integrate a second order system like this unless it's of a very specific form, especially if it has an arbitrary f of y, nonlinear f of y on the right hand side. So this will not work, but this, or the second order analog of this, will work. Okay, and that's what we will use for second order systems. Good. Okay, so let me get rid of this and say a couple. Now that we know what the physical significance is, let me say a couple of things about this pitchfork. So I have left it on here, and then we'll move on to a couple of examples so that things become a little bit more clearer, and the seemingly abstract or algebraic formulation that we've been going through actually has some utility. Okay, so let's get back to this for a second. Okay, to these two in particular. Okay, subcritical, supercritical. I'll tell you why that little distinction, not just of mirror image, but the change in stabilities, outer ones being stable, unstable, and so on. Why that has some physical consequence. Let's say I have a situation where I'm looking at a system, and let's say I have the following situation. Let's say I have this. I have 3 of these points. The middle one is stable. These 2 are unstable. Okay, let's do the same interpretation we did over there for the 2 fixed point system for this case. This is for the subcritical case. This is for the supercritical case. You have 1, again 2, and 3. Okay, stable, stable, unstable. When 3 exist. Okay. Now let's say I'm doing an experiment. I have a box. This is my experiment again. Right now I'm not telling you what these experiments are. This is an abstracted version of some experiment, and then you're measuring something out. You're measuring a voltage, let's say, as t goes to infinity, and you have a knob. This is our favorite experiment. We'll keep doing this. This is the maths course version of an experiment. and we'll keep doing this repeatedly. So let's say I have this device, something is going on and I'm measuring, I have some knob which I can tune, some lambda, knob corresponds to lambda, and I'm measuring a V that corresponds to my Y star. So the voltage as t goes to infinity that I'm measuring corresponds to my Y star. Okay. And presumably the transients in this case are extremely fast. So if you change the knob, presumably this time dependent thing that is happening inside this experiment happens very quickly, and what you're actually measuring is t goes to infinity of that experiment. Okay. So that's the setup. It's a sort of cooked up setup, but yeah, okay, it works. So I'm measuring Y star. Now let's start the experiment with the supercritical case. Let's assume the system I'm studying, the physical system on which the experiment is being done, has a, is a supercritical system. It shows a supercritical bifurcation, let's say. So I rotate lambda from negative values, I come towards the positive, and let's say my initial condition was somewhere over here, okay, somewhere equivalent to this point. Shouldn't draw a dotted line, maybe here, somewhere here, initial condition, okay. So I start the experiment, let's say at lambda very large, somewhere over here, large negative. I start the experiment, I change the knob little bit. I start with this initial condition somewhere at this point, y equals this point, turn the knob a little bit, get the output. What will the output be? The output will be the equivalent Y star. The transients will all happen, the trajectory will all start and do its stuff. So if this was the phase space on the left hand side, we only have the origin fixed point, and if my initial location was here, this is the origin, that corresponds to this fixed point. If my initial starting point is here, t goes to infinity, this system which starts here will go and reach the stable fixed point, right? We just discussed that. So I have my knob, I'm rotating it little by little, I'm coming from here, front. Every time I measure, the output I measure is 0, because Y star is the output, and because Y star is the output, any trajectory that is started here is 0. So if I start here, it's 0, I turn it a little bit, now the initial condition is still at 0, 0 is a fixed point, right? And so initial condition is at 0, it still stays at 0. Rotate a little bit more, it's still initially at 0 now, because all the transient is gone first itself when I started the experiment. It's still at 0, I rotate, 0, rotate, 0, rotate, so on. The moment I come to lambda equals 0, which is the bifurcation point, suddenly you start seeing something happening. Now the system whose initial state now is exactly 0, because the experiment is continuous, and the first time I started, let's say this is my initial lambda I, the first time I started with y naught, but the same experiment I am not restarting, I am just continuing by changing lambda. So the first time I started at lambda equals lambda I get 0, I get the steady state even though I started from y naught, I get 0. I am still at 0, I rotate lambda, nothing happens, I am going. When lambda comes to 0, okay, the y whose initial state now is 0, okay, not y naught, because at 0 I have gone through this entire branch. Now all of a sudden the origin becomes unstable at lambda equals 0. So the solution will now shoot up slowly, though, here it will shoot up a little bit, here it will shoot up a little bit, to another branch, either the top one or the bottom one. It's perfectly symmetric, so it will choose one or the other, doesn't matter, but it has to choose one. It will choose, let's say it chooses the top for whatever reason, okay. So my output, I was turning lambda and my output is still 0, and suddenly at lambda equals 0, the output becomes proportional to square root of lambda, and then after that point, as I keep increasing the knob, as I keep rotating the knob, the output goes up as square root of lambda. It's no longer 0, but I start measuring the square root of lambda output, okay. That's what will happen in a supercritical. If the system, this experiment, the physical system behind this experiment was showing a supercritical bifurcation. So you will suddenly start seeing a continuous change in the output, okay. Good. Let's do the same experiment here, okay. Again, I start at lambda equals lambda I. Now let's say I have a different system. That system shows a subcritical type of bifurcation. It's a property of the system. Remember, it's a property of the right hand side of the ODE. So I start with this. I'm slowly changing the knob from lambda I. what happens? Again, I use the same initial condition. Now, what is the situation? The situation is this. This is the situation. So, I have the initial condition here for a subcritical case. I turn lambda a little bit. So, initially when I am at lambda equals lambda, I stop the experiment. I start at y equals y naught. It immediately comes to the fixed point. Origin is a stable fixed point. It comes to the origin. So, it is at 0. It comes to 0. Output I measure is 0. Then I tweak the lambda a little bit. It's starting at 0 because it's already reached the fixed point. I'm measuring t goes to infinity, and it still gives me 0. So, I tweak 0, 0, 0, 0, 0 because that's always a stable branch. The moment I come to lambda equals 0, analogous to this, what happened here? When I came to lambda equals 0, slowly it started increasing in proportion to square root lambda, right? The output slowly started increasing with lambda. The moment I come to lambda equals 0 in this case, something very strange happens. Okay? When I just cross the lambda equals 0 point, all of a sudden the origin is unstable. Origin is unstable here as well. It's unstable here as well. But there is a key difference. Here, the solution now had two close by stable points to go to, stable fixed points to go to, the plus branch and the minus branch. But here it doesn't. So, the moment you cross lambda equals 0 in this case, if the system is subcritical, it will shoot off to infinity, plus infinity or minus infinity. Okay? So, that is an important distinction. In this case, continuously stuff changes. In this case, there is a sudden jump from one to the other. Okay? So, in the assignment, I will give you an extension of the subcritical bifurcation, which explains a phenomenon called hysteresis, which happens in the subcritical case, does not happen over there, and I will sort of help you work through this hysteresis problem. It happens when you have a right hand side that has a fifth order term in addition to the third order term. Okay? So, that is the important distinction, but basically this is the distinction that you see between a subcritical and a supercritical. Good. All right. So, that gives us some idea of why these fixed points and the stability is important, because it tells us something about the long term behavior of the solution, and this technique, both the linearization and the stability analysis, is fairly general enough that we can apply it to second order and higher. Okay. So, that is something we want to keep in mind. Good. So, now finally, let us put it all together and do a couple of examples. Okay. The first example I am going to work out is something that everybody is familiar with. Let us say this is me, and I have jumped off a helicopter for whatever reasons. Maybe I like to do that all the time, and I am falling. Okay. I am falling down. This is, of course, gravity is down, so that is a problem. And I start off with a 0 velocity or some initial velocity when I am jumping off, and I am falling down, but there is a difference, which is that I have a parachute. Yeah. So, there is air resistance to me falling, and that air resistance is given by, let us say, kV square. V is my velocity at any instant. Okay. So, I can write down Newton's second law for me. Of course, I can do that when I am falling as well, and it will look like this. The acceleration times the mass will be, because there is one acceleration constant that is due to gravity and the other one is opposing gravity, so it will be upward. Okay. So, I am going to get rid of this. I am going to just call that P dot equals G minus, let me just call this K tilde, and K tilde by M I am just going to call K. Okay. So, this is my equation. So, this is dV by dt. Okay. Now you can find the fixed points for this equation. This is the first order differential equation, of course. This is non-linear because it has b square. It's autonomous because it doesn't have t explicitly. So you can find the fixed point for this, which is just g minus kv square is equal to 0, and this gives v is equal to plus or minus square root of g by k. Okay, so that gives the fixed point. And you can find the stability of these fixed points by doing the right hand side df by dy at y star, and that is just minus 2k times v. So the fixed point that has the positive sign, so this can be v star, let me call this v star, fixed point. So v star is equal to square root of g by k is stable, because minus 2 times positive will be negative. So that will be stable, and v star equals minus square root of g by k will be unstable. Okay, you've probably seen this example before. I mean, it's something you've probably done in first year undergraduate or whatever. You calculate this. Incidentally, this is called the terminal velocity, right? You've probably done this before, but this is a slightly different way of looking at it. Okay, in the context of whatever we've discussed so far. So v, remember, v is positive downward because g is positive downward. So minus kv square is upward, so it's taken to be negative. So the v positive downward is a stable branch. V negative downward or v upward is an unstable branch. So you in principle can have two fixed points. If you draw the phase space, okay, this is what it looks like. It's a little bit artificial. The upward velocity really doesn't make any sense, because this, if velocity is upward, that will change sign, but still purely from an algebraic point of view, this is what it looks like. But the physically relevant branch is actually stable. So for any value in the vicinity of this, if you start and you're presumably going to jump downward, so for any value if you start this way, you will always approach and reach the steady state velocity. This is the terminal velocity as you come down and hopefully reach the ground or whatever. Okay, so this is the sort of physical interpretation of this case. You have one stable fixed point, again purely based on linearization and all of this stuff, and you don't need to do this integral to get this information. You can just look at the right hand side and do this stuff, and it's easy enough. Fixed points are easy enough to solve because you only have a quadratic on the right hand side. Okay, simple example. Now you could think of a situation where I'm changing g, just an artificial situation where I'm changing g, making it up, down, and so on, and you can do the usual stuff. This is a standard saddle node bifurcation normal form, so it will have those details algebraically, but physically they don't make any sense in this context, so we won't discuss them. Okay, so that's important. Good. So that's a fairly straightforward, reasonably trivial example. Let's look at another one. It's slightly more complicated, and I'll give you more complicated examples in the assignment. There's something called a logistic equation, and this is for population growth. So let's say I have a forest. This is my version of a forest, and the forest has some animals, whatever. I'm going to mark them by circles. Okay, and the animals are constantly growing. There are more animals being added. They're multiplying, and the rate at which they multiply, let me call the number of animals as n. Okay, the rate at which they grow is dn by dt, and that is r times n. Just a simple assumption, it's just if nothing happens, it's just exponentially it will grow, right. So, that is a good approximation for free growth. This is called the growth rate, of course, and this is called the rate at which the population increases. But simultaneous with this growth, the amount of resources that are available for these animals to use, for example, this could be like deer or whatever, and then you have some food that is available for this population of deer, and as they grow, more of them are competing for the food and fewer have access to food on a continuous basis, so they start dying. Okay. So, the population starts reducing, and so you can write down an expression for the death rate. These are of course models, they are not, they are very simple models. Ecology, there are lots of complicated models that build on this and make various generalizations, but this is a simple model that illustrates some of these ideas we have discussed. The death rate is given by minus r n square by k. Okay, that is a model, again it is an expression that people have used before to model the growth of these populations. Okay. So, you combine them together, you will get dn by dt is increased by the birth of new individuals and it is lowered by the death of subsequent individuals. So, you can bring this out, you will have 1 minus n by k, this is dn by dt. Okay. This fellow is called the logistic equation. And it is a nonlinear equation, of course, it has n square, the second term. So, it is a nonlinear ODE, can be, you can just bring it down to the other side and presumably cross multiply, integrate and solve. But let us try to apply some of the stuff about fixed points and so on that we have studied so far. So, the first of the 3-step process is find the fixed points of this equation. Remember, n denotes the population at any given point of time. So, I want to know, okay, what happens to the population as n goes to infinity, sorry, as t goes to infinity. Okay, what happens to the population as t goes to infinity? Are they all going to die or will some survive? Okay, that is a question you can ask. Let us look at the answer to that. The fixed points are of course right hand side equals 0. So, either n equals 0, they are all dead, or n equals k. That is the maximum number that can survive. You cannot have, there is no solution, there is no fixed point for n greater than k, okay, unless it is infinity. So, that is another question that this will answer. Can you suddenly have infinite of them? And already you are starting to see that it is probably not possible, because if you have infinite of them, the amount of resources is limited and the growth rate is proportional to n, death rate is proportional to n square. So, as n becomes larger and larger, the death rate starts catching up with the growth rate very quickly. So, stuff will start dying. So, already logically speaking, from the logistic equation, you sort of do not expect an infinite population to survive, but we will see what comes out. We are doing again the same set of algebraic steps that we have done for the usual case. Found the fixed points, let us do the linearization. So, you have df by dy. In this case, n is like your y, f is like the right hand side. So, this is just r minus 2r by k, 2rn by k, and this should be done at y star. Take the right hand side, take a derivative with respect to n is like a y, right. So, that is what this is. And if you do this, we have to now evaluate this at 2 different points, 2 different fixed points. So, you do that in step number 3 for n star equals 0, df by dy is just r, and remember r is a positive constant because this is the growth. So, r is positive, k is also positive. Because r is positive, k is positive, death has to be negative. So, that checks out. So, when n star is 0, df by dy, whatever, I am just going to use the same notation, but yeah, okay, whatever, is r. So, this is greater than 0 when n star is 0. Okay. So, this is unstable. So n star equals 0 is unstable. That's good. That's a good sign, because that means that there will never be a situation when you reach n star equals 0. It's an unstable point, unstable fixed point. So the population will never die out completely. No matter how steep the growth rate is, the population will never die. Okay, as long as r is positive, and that's okay. That's by definition r is positive. What about n star equals k? N star equals k. Df by dy is r minus 2r times k by k, r minus 2r, which is minus r, which is less than 0. So this is stable. Okay, so you have two fixed points. One fixed point is unstable, the other fixed point is stable, as we should expect. We already discussed the fact that when fixed points come in pairs, they should have opposite stability. So that's good, that checks out. What is the physical significance of this? Well, it's quite obvious now. You look at the phase space, which is n. You have two fixed points, one at the origin, unstable, and one at n equals k, n star equals k, positive. So there's no negative values here. It doesn't make any sense for n to be negative. So there's no negative population business going on. And so this part of phase space is never really reached by any trajectory. You always have to start at positive n. So wherever you start, let's say I start here or here or here, I'm eventually going to reach this value, okay, because it's a stable fixed point. On the contrary, if I start very far away, close to infinity, I just stuff the whole forest up with these animals, put in very, very, very large, and then I let them just do their stuff, that will also eventually reach the fixed point, because there's no other fixed point beyond this. Okay, there are only two fixed points. It's a second order polynomial, the right hand side, right? So you have only two solutions. So this will also come towards this fixed point. So no matter what I do, I will always eventually reach this population limit. Okay. And that's good, because then that tells you this is it's a happy system, because it reaches a finite value of n. Now this value k incidentally is called the carrying capacity of the forest. Okay, it tells you what is the maximum population the thing can sustain in the long term. Okay. And so irrespective of where you start, you're always going to reach that carrying capacity at some point as t goes to infinity. So that's a stable node, and okay, everything checks out. This is the physical interpretation in this case. Now in both of these situations, unfortunately, there is no scope for doing any bifurcation analysis, because the parameters don't really make sense. If you had r less than 0, for example, that doesn't make sense. It's not a growth. If you have r less than 0, it's like death, which makes no sense. Similarly, for k, negative really doesn't make sense, because n is always positive. So you always need to have these two parameters positive, and there's really nothing you will get from a bifurcation analysis. Even though in principle, algebraically you can do a bifurcation analysis for this problem, physically it doesn't make sense. So that is again something that you should keep in mind. It's always possible to algebraically get bifurcation point in some sense if they exist, by just manipulating the right hand side of the equation, but they have to make physical sense to be of some use. But the stability, fixed points and so on are usually always have a physical significance. They tell you something about the long term behavior of the solution. Okay. Good. So let's summarize what we've learned about first order systems. I think with this we're more or less done with first order systems. There's really not much more else to say, and I will summarize the key ideas that we should be familiar with, so that we know exactly where they come from and what we can do with them. So what did we do? Well, first we spoke about this linear first order we spoke about the homogeneous case, which is easily solved. This is just dy by dt is equal to some a of t times y, and we said you can solve the non-homogeneous case. This is dy by dt, again a of t y plus b or plus whatever, right, plus p of t y plus q of t equals 0, a is minus p, whatever. And we said that the general solution to this was the y homogeneous solution plus what we call the particular integral, and this one we got by just taking u of t y h of t. Y h we could get by solving this straight away. Okay, just you have to integrate. You have ln, you get e to the power of y h was just equals c e to the power of integral a of t dt. That's what y h was. Depending on a, you could integrate it and get a value. And from y h you could get y p by doing this, putting this back in, and then you got the equivalent of the integration factor solution, and that total general solution was given by this. Okay. Now, the next thing that we realized was that linear systems are fine, but then, and that basically exhausts all possible linear first order ODEs. Okay. Any linear first order ODE, you can just do this procedure and get a solution. And then we went to this nonlinear business. We first spoke about phase space. We said that okay, there are some certain situations in which you could get some type of closed form solution for a nonlinear ODE. There are maybe special cases, you do special transformations, special substitutions and so on. So, it is possible, but usually happens on a case by case basis, and we really are interested in more general principles than specific equations at this point, especially for first order. So, we introduced this idea of a phase space. This was a line, right? This was all possible values of y, just a single line. And then we went about finding, talked about stability of fixed points. We had this 3-step procedure, including linearization. Okay. And then we saw we looked at a situation where the right hand side depended on a parameter, and then changing the parameter presumably changed the nature of the solutions, changed number of fixed points or stability of the fixed points or something of that sort. We call those bifurcation phenomena, and then we identified how to look at bifurcation phenomena, how to get bifurcation points and so on. These are points where the solution changes nature qualitatively, and so we could work that out. And then we looked at basically what this means, so implications for physical systems. And I told you, I gave you a couple of examples and so on, but basically this could tell you that t goes to infinity or long term, or t goes to t1, whatever, right, that type of behavior. So, if you are interested in only understanding what happens in long term, you are not interested in the transients, then this is a perfectly well suited technique for your particular case. You can just look at it and look at the fixed points, look at the stability, and say what is going to happen. Okay. So, that basically wraps up most of, in my opinion, the interesting stuff about first order ODEs. The fact that we could take any higher order ODE and cast it into this form, again going back to this column vector notation. For the autonomous case, let us say, you could cast any equation of this form, second order, third order and so on, by making those substitutions. We discussed that earlier. And the idea of a phase space can then naturally be extended into these systems. So, whenever you are stuck with a problem with the linear system, you can actually start doing this phase space business a little bit better, and it will give you again some information about fixed point, stability, bifurcation. You can do the same exercise all over again. It will have significance again for t goes to infinity solutions and so on. So, this entire procedure that we introduced will naturally carry over to this. It becomes algebraically a little bit more complex, but yeah, it naturally logically carries over. Okay. So, that is the whole motivation for doing this. And again, right at the start hierarchy, you start from exact solution, quadrature, qualitative stuff, and then numerics. Okay. I haven't said anything about numerics for first order equations because they are not that interesting, but I will talk about numerical schemes, RK4 and so on at the end when we finish discussing second order systems. Okay. So, we will spend one session on numerical schemes for solving initial value problems. Boundary value problems are more complicated numerically also. So, we will just look at initial value problems. Good. What is next? So, the next step is naturally to graduate from first order systems to second order systems, and that is where really all the action is. Okay, that is where most interesting stuff happens. You start seeing oscillation. Remember also we said that from this phase space, just using geometric arguments, we could argue that first order autonomous system will never show any oscillations at all whatsoever. Autonomous is the key word, okay, because the phase space is linear, and so it is just going to go off in one direction or the other, you can't oscillate. But next step will be to look at second order systems. Okay, we will look first at linear second order systems, linear constant coefficient, actually just linear, let us start with just linear. And unlike the first order system, you cannot write down an expression for a solution for a second order linear system, arbitrary second order linear system. Okay. So, it presumably looks like this, d square y by dt square plus p of t dy by dt. This is presumably the second order linear system, general form p, q and r are arbitrary functions of t. For the first order system, we could write down an expression using the integration factor y h, y c and so on. At least we had an expression. So, if you could evaluate the integral in some way, then you get an expression for the solution, right. For the second order case, you cannot do that. Okay. And obviously, you cannot do that because you have a second derivative, you can't just multiply by an integrating factor. So, already the complication has become quite severe. I mean, the most simplest example in the first order case we could solve, at least write down an expression, but now we can't do that. So, the range of techniques that you have just for linear second order ODEs, are extremely vast. Okay, there are lots of variations that you can use. We will look at some of them, including, as I mentioned at the start, a series solution for certain special cases. And series solutions are important because they appear multiple times in practical situations. I will give you examples of that in the case of spherical harmonics, in the case of Laguerre equations, Legendre equations, whatever, all of them. Okay. So, they are extremely useful from a practical point of view, and so that is one recourse we can take that we did not have to do for the first order case because it was fairly standard. Excuse me. The only time you can solve a second order linear equation is when the coefficients are constant. It is fairly standard, you have probably done that before. We will go through that quickly. So, that is one subclass of linear second order ODEs that we can solve. And then we will see how to use that solution in a general case when you have, let us say, a non-homogeneous but constant coefficient case. You can again use that YH plus YP thing we introduced. We can do the solution, you will be fine. But in the general case, you can't. Okay. So, we will spend a good amount of time on the linear second order ODE. I will give you some results that show you how complex this system actually is, even though it seemingly looks fairly trivial. We will start with that, and then we will progress to non-linear second order ODEs. Okay. Unfortunately, this is a big business by itself. It's probably can be a content of an entire course, and so we will only touch upon the basic ideas. We will talk about again the same 3-point scheme that we use for first order. We can carry through, like I said. You can do fixed points. You can find the fixed points. The definition changes a little bit if you have a non-linear system in second order non-linear system, but you can still find fixed points. You can find the linearized version about fixed points analogous to the 1D case. We will do that as well. And you can use that information to now find the stability of fixed points. This is where things start becoming interesting, because now phase space becomes a plane as opposed to a line. So, like we mentioned with this ant fellow who was crawling on that line a little while ago, the trajectory can now start going outside a line and start doing things in the plane, and so you can start seeing oscillations now all of a sudden. And so the nature of the fixed points, the types of fixed points you can get also grows. You don't just have stable, unstable and saddle like we had in 1D. You can have other things. You can have centers about which oscillations happen. You can have centers about which spirals happen, stable spirals, unstable spirals. All of that will come up. So it's richer in that sense. And the linearization also will be a little bit more algebraically complex. Instead of just looking at the sign of df by dy, you have to evaluate a determinant and a trace of a matrix. Okay, that's the only change. Presumably by now everybody knows everything about determinants and matrices and traces and so on. So it should be, and these are 2 by 2 matrices. It's probably the simplest matrix you can get, and so it should be fairly straightforward to evaluate many of these things. Okay, so we'll see how to do that. We'll see how to understand nonlinear systems. I'll touch a little bit about bifurcations at the end, because this again comes up often, especially in problems in vibration and many times in mechanics problems as well, in solids and fluids and so on. So I'll touch upon bifurcations, pardon me, a little bit right at the end, but I don't think we'll have too much time to cover it in any detail. But at the end, when we do this, at the end of this, I'll give you some brief introduction about numerical schemes. Okay, that will be the very last bit that we'll discuss. And this should give you some idea about how to estimate errors and things like that, which will come in handy if you ever sit down and write your own numerical scheme, which is recommended at some point if you want to solve an ODE. Okay, so that's the broad outline for the next maybe 4 or 5 sessions. Okay.